Okay, so today we're going to study surfaces with kx and f, and this will be the end of our classification for surfaces. So let me start with a definition. A minimal model, in the case of surfaces, is a smooth projective surface X whose canonical bundle is F. So in particular, a minimal model is a minimal surface. It can't have any -1 curves, but this is stronger. It also means that we're not in this condition where we're not in this situation where we're a P1 bundle or a rational surface. Okay, so another way to phrase the goal of this week is to study minimal models in dimension 2, and essentially where the name of this field comes from. Okay, so the first important theorem, I'll call it the non-vanishing theorem, though this isn't really, I'll call it this because by analogy with the theorem that we'll prove in higher dimensions later. So suppose kx is F. Then there exists some integer m such that the pluricanonical divisor mkx has sections. And so that's why I called it the non-vanishing theorem. There's a non-vanishing theorem in higher dimensions that also gives a condition for H0 to be non-zero for some multiple. So this one is much more classical, but I called it that by analogy. So that's somehow the first important point for studying these minimal models, which already tells us an important dichotomy and an important coarse classification of surfaces as a corollary. If kx is an F, then the Kodaira dimension is non-negative because we have sections. So this gives us a coarse classification of surfaces by Kodaira dimension, which essentially says that every surface X is birational to a minimal surface by a sequence of blowdowns where xm is a minimal model if and only if the Kodaira dimension of X is non-negative and xm is ruled or rational, or P2, if and only if Kodaira dimension of X is -infinity. So this gives us the other direction of what we proved last time, which was that if you end up in the ruled or P2 case, then you have Kodaira dimension -infinity, and the non-vanishing theorem gives us the converse. Okay, so this is really nice because it says that the Kodaira dimension really determines the behavior of our surface under running this minimal model program where we're contracting these -1 curves. And then the next very important theorem is the abundance theorem, which really follows from the non-vanishing in this case. Which says that once you know that the canonical bundle has sections, then actually it has a lot of sections. So it tells us that if kx is an F, then kx is semi-ample. i.e. mkx is base point free for some m. Okay, so those will be our goals for this week, proving these or sketching the proofs of these theorems. So I'll make one remark, which is that once you have abundance, this leads to a classification of surfaces by Kodaira dimension. Because once you know that Kx is semi-ample, then for each Kodaira dimension, you can try to study what does this linear series look like based on what the dimension of the image is. But the kind of unfortunate state of affairs is that you essentially need to run through the classification of surfaces and do case-by-case work to actually prove these theorems. So somehow the best thing you could hope for is that you can give some direct proof of non-vanishing and abundance, some kind of abstract proof that just says it has to be true, and then use that to produce the classification. But it turns out that to actually prove these, or the only proofs that we know of for these theorems, even in the case of surfaces, is to actually go through all the possible cases. And then maybe the other remark is that the abundance conjecture in higher dimensions is one of the big open conjectures of the field, and we'll talk about it in its generalizations later in the course. Okay, so I want to start with some preliminaries. That we'll need while proving these theorems. So first, let me talk about big divisors and the Ataka dimension. So the Ataka dimension is a generalization of the Kodaira dimension to other divisors. So if L is a Cartier divisor on X, for now you can still think that X is, say, smooth and projective. Maybe more generally, these statements hold if X is normal instead of smooth. We'll define the Ataka dimension of L as the maximum of the dimensions of the images of the linear series ML and now I have to be a little careful and explain what is this maximum over. Well, it's the maximum over all the M's where ML is effective. So let me give a definition. N of L, the semigroup of L, is the subset of the integers, or of the natural numbers, where ML is not empty. It's the numerical semigroup of L. And so this maximum is over all integers in N. Otherwise, it doesn't really make sense to talk about the image of the map phi. And then by definition, this is less than or equal to the dimension of X. And of course, if we plug in the canonical divisor, then we just get the Kodaira dimension of X by definition. Okay, and now a proposition. By the way, all of this, for reference, you can look at the book Positivity in Algebraic Geometry 1 by Lazarsfeld. And I've been putting references up on the website as well. Okay, so the first proposition, L has dimension kappa if and only if there exist constants, little a and big A, such that for all m in the semigroup large enough, we have the following bounds. A m to the kappa is less than or equal to the dimension of the global sections of this bundle, and is less than or equal to capital A m to the kappa. So it's saying that this that another way to talk about this Itaka dimension of a line bundle is that it's measuring the growth rate of the global sections for large m in the semigroup, for large m where the global sections are non-empty. Okay, and then I can find big divisors. L is big if this dimension is maximal. Which by our proposition happens if and only if this has growth rate at least m to the dimension, but that's also the biggest growth rate you can have, so we just need one side of the inequality. Okay. And now the point of all this is that we'll use a few properties of the big divisors during the proofs of non-vanishing and abundance for surfaces, but also we'll need to study big divisors in higher dimensions as well. So the two properties, one of them is Kodaire's lemma. Suppose D is a big divisor and E is effective. Then the global sections of MD minus E are non-zero for M large enough in the semigroup. This should be believable at least, because being big means that OX of MD has a lot of sections for M large. And so now we're saying that, in fact, it has so many sections that you can find ones that vanish along any effective divisor if you make M large enough. That's exactly what the statement is saying. But as a corollary of this, we have an important equivalent characterization of being big. So D is big is equivalent to saying that there exists an ample A such that D is A plus N, where N is effective. So the slogan here is that big divisors are the same as divisors of the form ample plus effective. So you should think of them as being close to ample. So one direction here just comes from the definition. If A is ample, then it has a lot of sections. It has the appropriate growth rate. And if we add an effective to it, then we're just adding even more sections. So D will still have a lot of sections, so it'll still be big. And so the the interesting part of this is the opposite, that if D is big, then you can write it as ample plus effective, and that comes from Kodyr's lemma. Okay, and then the other corollary that we'll use all the time is if D is nef, then we have a numerical characterization of being big. Then D is big if and only if the top intersection product, this number, is greater than 0. So for now, we're only going to work with surfaces, and then I'll review kind of intersections of divisors and higher dimensions a little later for people that haven't seen it. But this statement is essentially Riemann rock, or some asymptotic Riemann rock in higher dimensions. And the important corollary for this week is that if X is a minimal surface, or a minimal model in dimension 2, so Kx is nef, then we have this numerical criterion for the Kodaira dimension. Then the Kodaira dimension of X is 2, if and only if Kx squared is greater than 0. So that's really the statement that we're going to use a bunch of times today and Wednesday. The other background thing that we'll need is the notion of the Albanese morphism. Okay, so let me just write a theorem listing all the properties. Let X be a smooth projective variety. Then there exists an abelian variety. Alb of X, the Albanese variety, and a morphism alpha from X to alb of X, satisfying a certain universal property. So basically, if beta is any other morphism to an abelian variety, there exists a factorization through alpha. So the Albanese is the initial abelian variety that X maps to. 2, alpha is an isomorphism on differential forms. So if we look at the pullback from H0 of omega 1, then this is an isomorphism. So in particular, this tells us that the dimension of the Albanese is the dimension of H0 omega 1, which is usually denoted H10, which is, for surfaces at least, called the irregularity. Really, I should say, by Hodge symmetries is the same as H01, and maybe that's more commonly called the irregularity. From this universal property, we immediately get that as a group, Albanese of X is generated by alpha of x. Because if you look at the abelian subvariety generated by the image of x, that'll give some factorization of alpha, but by the universal property, the Albanese is the initial one, so it has to be the whole thing. We also get functoriality. So if f from x to y is some morphism, then we have a commutative diagram like this. With the extra property using 3 that if f is surjective, then that implies that alpha of f is surjective. And then following special case that will come up a few times in the proof is that if x factors through some curve C, so basically if the image of the Albanese is a curve, and then we can take its normalization because x is smooth, so I'll factor through the normalization. Then the Albanese of x has to be the Jacobian of C. And so in particular, the genus of C is the same as this regularity. Okay, let me maybe scroll through all those parts again. So in general, what are abelian varieties over the complex numbers? Well, we can start off with some complex torus, which is of the form V mod gamma, where V is a complex vector space. Gamma is some integer lattice. And then we want it to be algebraic, so we need to include some polarization or ample line bundle to make it projective. And then the important fact is that any morphism between these complex tori, we call it U, any such U up to translation in the group structure on T, or equivalently on this vector space mod gamma, is induced by just a linear map between vector spaces. So by some linear map A, that preserves the lattices. And so basically, to construct this Albanese and prove these universal properties, we just have to construct a vector space and a lattice with the polarization, and then use this fact to prove the universal property. So maybe the other thing I should say then is that this fact implies that if we look at the pullback under this U, of differentials, sorry, I should write T2 here. Well, if we look at this quotient presentation, tangent vectors are the same as this vector space V, and so differentials are its dual. So this is V2 dual, this is V1 dual, and this fact tells us that the map here is pulled back by this linear map A. And so basically saying up to translation, we can describe maps between abelian varieties as linear maps, and we can understand the pullback on differentials is just the dual linear map. So that's some other key input. Okay, so now we just need to give a definition. So Albanese of X is the following complex torus. We take H0x omega 1 X dual, again, because we want H0 of omega 1 of Albanese to be the same as that on X. So we take the dual as our vector space that we're quotienting by. And we mod out by the lattice H, where H is the image of a natural map from H1 lower 1 XZ into H0 X omega 1 dual. And what's this map? Well, we take a cycle, gamma, and we send it to the functional that takes in a differential and maps it to the number, the integral of omega over gamma, which is some complex number. So that's this map. That gives us a lattice inside of H0 of omega 1 dual. So we can take its quotient. This gives us an abelian variety. And then the polarization comes from Hodge theory, which I won't say more about. So that this complex torus is really algebraic. It's really an abelian variety. Okay, so now we want to define a map from X with Albanese, and to do that, I can just draw a picture. So pick a base point. This map will end up depending on the base point, and choosing different base points will correspond to translating on this Albanese. So let's pick a base point P, and then alpha of X is defined by picking some path Cx from this point P to this point X. And then we need to give a functional on differentials. So we'll define this to be the map omega maps to the integral along this path. And now if we pick some different path over here, well, then the composition is some loop in H1. And so by definition, this maps to 0 inside of the Albanese because the Albanese is the quotient by this H1. And so this alpha is well defined, independent of the choice of this path. So that's the map. And then now you use this fact to check all the properties of the Albanese. Okay, so that was the background that we'll use during the proof of these two theorems. So let me start with the proof of non-vanishing. So let's recall what we're trying to prove is that if X is a minimal model, in dimension 2, then some multiple of the canonical has a section. Or another way to say it is that the canonical, if the canonical is Neff, then it's really in the effective cone. As a Q divisor. Okay, so let's start with a lemma. Suppose Kx is Neff, and the Kodaira dimension is less than or equal to 0. Then the Euler characteristic of O is non-negative. This will come in handy when we apply Riemann-Roch many times. Okay, so under these assumptions, then Kx is Neff, but not big. So that means that Kx squared is 0. And now we can plug into Noether's formula, which I used the other day, but didn't really write down carefully. But it's some variant of here's a Riemann-Roch. So the version that we want is that 12 times the Euler characteristic is equal to Kx squared plus the topological Euler number of X. So this is topological. Okay, and now we know that this is 0. So this is just E of X, which by definition is B0 minus B1 plus B2 minus B3 plus B4, where these are the dimensions of the singular cohomology groups, or the Betti numbers. And now by Poincare duality, we know like B1 is the same as B3, and then B0 is the same as B4 is just 1. So we can rewrite this as 2 from the B0 and the B4, and then minus 2B1, which I'll write it as 2 times 1 minus B1, plus B2. Okay, so 12 times the Euler characteristic of O is the same as 2 times 1 minus B1 plus B2. On the other hand, let's write down the Euler characteristic of O under these assumptions. So this is always 1. And this is H0 of OXK by Serre duality, but this is at most 1 because of our assumption that the Kodaira dimension is less than or equal to 0. So all of this is, yeah, okay. Then we can also write down B1. B1 is the same as H1 XOX plus H0 X omega 1 by the Hodge decomposition. And then by Hodge symmetries, this is the same as 2 times H1 X OX. Okay, so now putting these things together, we see chi of OX is less than or equal to 2 minus H1 of OX. That was this statement. And then we can plug into this Noether's formula. So this will be 2 minus 2H1 XOX plus the second Betti number, and then by this observation here, we get that this is 2 minus 4H1 XOX plus B2. And then using that, we get that H1 is greater than or equal to, minus H1 is greater than or equal to the Euler characteristic minus 2. So this whole thing is greater than or equal to this 2 plus 4 times the Euler characteristic minus 8 from this purple inequality plus B2. This is minus 6 plus 4 times the Euler characteristic plus B2. And so 8 times the Euler characteristic is greater than or equal to minus 6 plus B2 greater than or equal to minus 6. So the Euler characteristic is greater than or equal to minus 6 over 8, but it has to be an integer, so it's actually greater than or equal to 0. Ooh, okay, so that was some manipulations with a lot of different formulas. So one comment I'll make is that this looks like just some random inequality that happens to be true, but there is actually an interesting generalization to higher dimensions, which we won't need, but it's interesting to know that it's not really completely random. Okay, so now using this, we'll prove the non-vanishing. And the strategy, and maybe one indication that you need to use that it's not just some kind of abstract theorem, is that the proof is by contradiction. So we'll assume that we have some surface with kx nef, but Kodaira dimension minus infinity, and then try to use all these various inequalities and use the Albanese morphism to derive a contradiction. So suppose kx is nef, but that the Kodaira dimension is not greater than or equal to 0, which means it's minus infinity. Then we can apply this lemma. We know that the Euler characteristic is greater than or equal to 0. But we also know that this last term, which by Serre duality was OX of k, we also know that this last term is 0 because we're assuming that there are no sections for any powers of the canonical. So what this tells us is that 1 minus H1 XOX is greater than or equal to 0. We also know, so this number the other day, we defined these plurigenera. So this number is just the first plurigenus, P1. But we also know that all the plurigenera have to be 0. So these were the dimensions of all the powers of M. They all have to be 0 because we're assuming that we're in the negative Kodaira dimension case. So in particular, P2 has to be 0. But then we knew Castelnuovo's, we proved this criterion for irrationality. Last time, which implied that if P2 and H1 were 0, then the surface is rational. But in our case, we're assuming that the canonical is Neff, so the surface can't be rational. Because if it's rational, then we'll end up with P2 or P1 cross P1 when we run the minimal model, when we take the minimal surface, or actually Kx is Neff, so it's already minimal. So if it's rational, it has to be P2 or a P1 bundle over P1, and in both those cases, the canonical is not Neff. So this can't happen. Because Kx is Neff. So that tells us that since we know P2 has to be 0, that tells us that H1 can't be 0. And then our inequality tells us it has to be at most 1, so it has to be exactly 1. Okay, and now we can look at the Albanese morphism. So this is the same as H0 x omega 1x. And so now we have this Albanese morphism, which maps onto a one-dimensional abelian variety, which is another name for an elliptic curve. And now the strategy will be to derive a contradiction from this alpha. So roughly the idea is to say, using the properties of this Albanese morphism, we'll show that in fact the canonical does have sections, and that's a contradiction because we assumed it didn't have sections. So that's the very rough strategy. And I should say a few properties here. So alpha is surjective and with connected fibers. So in particular, it's flat because it's surjective and X is irreducible. And let's just denote by F the general fiber, or maybe a general fiber. That has to be some curve. Genus of this general fiber is at least 1. And essentially it's just a computation, so we know that F squared is 0 because it's the fiber of some map to a curve. And so now we use a junction. So we also know that Kx plus F intersected with F is the same as the canonical bundle of F. F squared is 0. Kx dot F is greater than or equal to 0 because Kx is Neff. So this is greater than or equal to 0. But if degree of K is greater than or equal to 0, then that implies that the genus is greater than or equal to 1. Okay, so then a much more subtle claim is that alpha is a smooth morphism. Which since we already know it's mapping onto a curve, and so it's flat, then this is the same as saying that all the fibers are actually smooth curves. Okay, so this is a little more tricky. So let's set some notation. So actually, no, let's prove first that the fibers are irreducible. So suppose that some fiber was reducible. So we could write it as F1 plus F2, where F1 and F2 are where the supports of F1 and F2 are not the same. So we'll draw a picture like that. Then if H is an ample, then you can check that the numerical classes of H, F1 and F2 are linearly independent. As numerical classes of divisors. Because this F1 and this F2 are fibers, so they're going to have negative self-intersection, but they're going to intersect each other in some positive number because the fibers are connected, so they have to intersect somewhere. And then H intersects both of them positively, and then also F1 plus F2 is a fiber, so it squares to 0, and so you use all these kind of relations to derive that they're linearly independent. So I'll leave that for you to check. But this tells us that the Picard rank is at least 3. And the Picard rank is less than or equal to the dimension of the singular cohomology, because we can view the intersection product as the cup product inside of the singular cohomology. So this is the second Benny number. But now we use our previous relations and we see that this topological Euler characteristic is 0, which we showed earlier was the same as 2 minus 4H1 XOX plus B2, but we know that that H1 is 1, so B2 has to be 2, and that's a contradiction. So we know the fibers are at least irreducible. Okay, so maybe I'll call this step 1. Okay, so step 2, we want to understand how non-reduced they can be and whether the reduced fiber has to be smooth. So let's write down some notation. Let's call alpha p reduced. Let's denote it by fp. And so the full fiber alpha inverse p will be some multiple of fp, depending on what point you're at. And we know that these are numerically equivalent to a general fiber f. And we also know by step 1 that fp is irreducible. Okay, so let me leave the following lemma as an exercise, which is a statement about curves. If you have any curve, in this case fp, but fp is some possibly singular curve, then the statement is that the topological Euler characteristic of fp is always greater than or equal to 2 times the Euler characteristic of the structure sheaf with equality if and only if FP is smooth. So just to convince yourselves, when FP is smooth, well, the topological Euler characteristic is 2 minus 2g, and that's the same as 2 times the Euler characteristic of O by Riemann-Roch in the smooth case. Or I guess Serre duality, really, but whatever. Okay. So there's some generalization that when we have singularities, the topological Euler characteristic just gets bigger. And the idea here is look at the normalization, which is smooth, try to understand how the Euler characteristic of the normalization changes, and also how the Euler characteristic of O changes under normalization. So next, we have some inequalities that you can use adjunction to compute. So the topological Euler characteristic of our fiber is greater than or equal to 2 times the Euler characteristic of O. That was this lemma. And then using adjunction and Riemann-Roch, you can compute that this is the same as 2 times 1 over m Euler characteristic of the full fiber. Of O of the fiber, essentially using that MP times FP is the fiber, and then that you can compute these things by intersecting using adjunction. So we get that MP there. And then our general fiber is smooth because we're in characteristic 0 and we have some morphism whose source is a smooth variety. So F is smooth. So again, by the lemma, this is the same as 1 over MP, the topological Euler characteristic of our general fiber. But then we also know that our general fiber has genus at least 1. Which tells us that its topological Euler characteristic is less than or equal to 0. So 1 over m times that is greater than or equal to the topological Euler characteristic. Okay, so the upshot is that when we get to these fibers that are non-reduced, the Euler characteristic can only get bigger. That's the important point. And now we use some properties of topological Euler characteristics to compute the topological Euler characteristic of X. So on the one hand, by Noether's formula, we already saw that E of X is 0 under our numerical conditions. On the other hand, we can compute the Euler characteristic by cutting up this according to this Albanese morphism. So we can write it as the Euler characteristic of the general fiber times the locus where the morphism is smooth. So E minus delta, where this is the discriminant of alpha. So we're just throwing out the points where the fibers are not smooth curves. Then such a morphism, we have this proper morphism that's smooth, so it's a fibration in topology, and so the Euler characteristic splits as a product. Plus, we need to add back in the Euler characteristic of these non-reduced fibers. And because it's a topological Euler characteristic, it doesn't care about the non-reduced structure. It's just E of the underlying reduced FP. And now we can rewrite this. We can throw back in these deltas, these points of delta. So we can rewrite this as EF, E of E, plus EFP minus E of F. So just for every point in delta, I've added back E of F into the first term and then subtracted it from the second term. But now this is 0 because E is an elliptic curve. And then each of these terms are greater than or equal to 0 by this lemma above. So the only way they can be 0 is if they're all actually equalities. Okay, and now once we have this equality, we also know that this is the same as 1 over MP E of F. So the only way that we can have these equalities are if either E of F is 0, and then the M doesn't do anything, or if all the M's are 1. So we have two cases. In this case, the genus is 1, or the genus is greater than or equal to 2, in which case the only way we can have these equalities is if M is 1. But now in the second case, then by the lemma, we actually get that once MP is 1, then we get that E of FP. I guess it's true in both cases, actually. In either case, once we have these equalities, we know the holomorphic, like the Euler characteristic of O, is constant. Yeah, I do need MP as 1. Yeah, so in this MP is 1 case, then because the Euler characteristic of O is constant in our family, then we get that this is 2 chi OFP, so FP is smooth. Okay, and then so in this case 2, we have, that should say genus is at least 2. In this case 2, we're done. We have a genus 2 family of curves where everything is smooth, every fiber is smooth and reduced. In this first case, we're going to see that that's actually not possible using Kodairo's canonical bundle formula. And we'll talk more about this on Wednesday, but I'll write down the theorem now. So let F from X to C be a minimal genus 1 fibration. So the generic fiber is a genus 1 curve, and there are no -1 curves in the fibers. And suppose that we have some non-reduced fibers. So let's say that we have non-reduced fibers M1, FP1 through MN, FPN. So this MI is greater than 1. And FP is the underlying reduced fiber, not necessarily irreducible. Then there's the following formula for the canonical bundle of X. It's given by first pulling back the canonical bundle on our curve, twisted by a certain line bundle. And then tensored by there we go. By a contribution from these non-reduced fibers. So we take O of Mi minus 1 times the non-reduced fiber. So in particular, if all the fibers are reduced, then this contribution's gone. And the other important property is that the degree of R1 F lower star OX dual is the same as the Euler characteristic of OX. Okay, so we'll talk more about this on Wednesday. This is a key input both in this proof, but also in actually then classifying Kodaira dimension 1 surfaces. So kind of after we know abundance, then we'll know that they're all elliptic vibrations, and you can use this to try to classify elliptic vibrations. But here the important point is that we know that chi OX is 0. And we know that C is an elliptic curve. So omega E is O. So this line bundle in the formula has degree 0 in our case. So if we had some non-reduced fibers, then we'd have some contribution here with Mi strictly bigger than 1. Which would imply that in our case, omega X is the pullback under this Albanese map of some degree 0 line bundle plus some degree strictly greater than 0 line bundle. Maybe if I take a large enough power. So I take a large enough power to multiply through so that kind of NFP is some multiple of the general fibers. Take some large enough power. Then this is the pullback of a degree 0 line bundle plus some degree greater than 0 line bundle supported on these fibers. So this is basically this has a lot of sections. Namely, the Ataka dimension is 1 because it's pullback of an ample on a curve. But that contradicts our assumption, which is that we're in the Kodaira dimension minus infinity case. So that's a contradiction. So even in this elliptic case, these m's have to all be 1, so that there's no term coming from non-reduced fibers in this formula. And then once we know the m's have to be 1, then this same remark holds here. And so in either case, we get that all the fibers are actually smooth. Okay, so that completes this step of the proof. So now, where are we? Let's recap. I'm not sure if I've lost track of my numbering. In my notes to step 3, I have no idea if I actually followed that. So now, what do we have? We have a morphism alpha from X to E, where alpha is a smooth family of genus greater than or equal to 1 curves, and the genus of E is 1. So that's where we're at. And now the final piece of the proof, there's a few different ways you can proceed from here. The classical argument is this very clever but involved argument of Enrique's, which came up in the original classification of surfaces, where you use this alpha to then produce a different fibration on X, which is an elliptic fibration with some nice properties, and then use the canonical bundle formula on that elliptic fibration to check that the canonical bundle actually does have sections. And then that'll be a contradiction. So that's the classical argument, but it's very involved. There's a different argument, which I'm going to give, but it uses a kind of a big hammer, which is the moduli space of curves. But I find this argument maybe easier to digest, even though you have to assume some big things. So the key point is the following theorem, which has 2 different analogous statements depending on whether the genus of the fibration is 1 or greater than or equal to 2. So suppose that alpha from X to E is a smooth and proper morphism with, well, I'll do the 2 cases in a second. So with genus of E less than or equal to 1, so either E is an elliptic curve or it's P1, then in the genus of the fiber at least 2 case, we have maybe the cleanest statement, which is that alpha is isotrivial, meaning that there exists some finite étale cover, some finite unramified E prime mapping to E, such that when you pull back and look at this alpha prime, this is actually isomorphic to the general fiber times this E prime. So alpha itself might not be a product, but after some finite cover, it becomes a product. So you should think of it as I started with some product and then I quotiented it out by some automorphisms on X prime. So that's the cleanest statement in the genus greater than or equal to 2 case. In the genus 1 case, we have to relax this a little bit. Here, we can't say that X itself becomes trivial when you pull back, but we can say the analogous statement that the line bundle alpha lower star of the relative canonical sheaf. So this is the sheaf. So when you restrict on each fiber, you get the canonical of that fiber. Then this is a torsion line bundle, which is equivalent to saying that there exists such a T, some finite étale T, such that the pullback of this alpha lower star omega is actually trivial. And using the same kind of diagram where we take the fiber product, this pullback by some cohomology and base change is the same as alpha prime lower star of the canonical for X prime. So basically saying in the genus 1 case, we don't have the stronger statement that the actual map becomes a product, but we have the slightly weaker but good enough for our purposes statement that the push forward of the relative canonical looks like it's coming from a product, that it's still just trivial.